Hello guys, in today's video we are going to talk about propagation and path loss model. See here in this graph. Imagine we are sending a signal. There will always be two sides, the transmitting side and the receiving side. And uh, if we take an example where the radio inside your car is the receiving side, the longer the distance or your car is going, if your car is going somewhere, the distance between the receiving side and the transmitting side will increase. Hence, the if we look at the graph, uh, the power of the receiving side will decrease slowly due to the distance. But if it if there is an obstacle between the receiving side and the transmission side, then the power of the receiving side will drop significantly faster. If you can see the red line in the graph, and then if the power received by the radio inside your car is not in the line of sight and is reflected uh, in multipath fading, then the power received by the radio will decrease even faster in respect of distance. This is called propagation characteristics. That is why we have path loss modeling, so that we can know how a signal is being transmitted, and then we can model a system so that it can be transmitted smoothly and correctly. The first one in path loss modeling is using Maxwell equation. But if we use a Maxwell equation, it is because of its impracticality in using Maxwell equation. We don't use, or we need a model that is easier to use, such as a free space model, Touré model, and other model. In this case, a ray tracing model. In the first picture above, we can see the on the picture on the left side, we can see that this is a free space model, or can be called as well line of sight model, because in between the receiving side and the transmission side there is no obstacle. And then for the middle, it's called a two-ray model, where the receiving side has two signal received in a loss or line of sight signal, and the other one is a signal where it is being reflected. The third one is a ray tracing model, where we use reflection, scattering, and diffraction to calculate all the possible paths of a signal. This requires a sight geometry and the properties, but it is easier than Maxwell, because we use geometry rather than a differential equation. The next one is a simplified path loss model that we use where there is a lot of reflection in the path loss. Such that like area with a lot of building and that can reflect the signal being transmitted. Next, we are going to talk about millimeter wave propagation, as it is important. It is an important topic, such that we can advance the wireless communication industry, where if you can see that the channel models are currently are imager, and based on measurement, there are only a few accurate analytical model, and there is a huge path loss proportional to the lambda squared in millimeter wave propagation, and even oxygen and rain can absorb or attenuate millimeter wave signal. Now, the next topic is empirical channel model, where earlier cellular empirical model uses extensive measurement is such that it is because empirical channel model is a model that is based on measurement. That is why for early cellular systems it is based on an extensive measurements. The next one is Okumura model, Hatta model, and then there is multi-slope model, and then Wolfish or Bertoni model. In current serial models, there is multi-path delay spread and user speed and MIMO antenna correlations, and then in Wi-Fi channel models, there is an indoor and outdoor path loss model. Thank you for watching.